Here we go. You gotta sign in, hold on. Okay, plan for today, twofold. That being to create a reinforcement learning algorithm for an assignment, and read up on the Signal protocol also for an assignment. And I would say that would take up most of my day today, but it'd be interesting. Okay. There is a consistent amount of dropped frames, which I'm concerned about. Yep. Just refamiliarizing myself with Vim again. Random choice of an action. Doesn't matter. You know, not the main objective there. So practical planning, EDDL, policy iteration or value iteration, Monte Carlo tree search or uniform cost search. Oh wait, uniform something. Okay, but we're doing reinforcement learning, classical, approximate, or deep Q learning. One thing I do want to search for is whether reinforcement learning classical what is classical reinforcement learning? I think a better way to search would be to use this. Okay, normal form games. MDP. Multi-arm bandit. Epsilon decreasing. It's taken from Torch. Interesting. Okay. Forward. Jupiter. At the author Tim Miller, University of Queensland. Alright, so what is reinforcement learning? The learning from experience is a branch of machine learning in which agents learn to make sequential decisions guided by a set of rewards and penalties. It differs from traditional supervised machine learning in a few ways, primarily experience instead of labels. In traditional supervised machine learning, we need to provide examples that contain inputs and labeled outputs. In reinforcement learning, the labels are provided by the environment and the agent interacts with the environment. These labels are called rewards. Rewards can be positive, which means our agent will try to learn behavior that leads to positive rewards, or rewards can be negative, which means our agent will try to learn behavior that leads to negative rewards. The aim is to learn behavior that increases the cumulative reward over a number of decisions. Decisions are sequential. Reinforcement learning is sequential decision making. This means that agents need to make a series of decisions over time, with each decision affecting future outcomes. Feedback in the form of positive, negative rewards is received at each step, although the reward may be zero at most steps. but in most situations, simply maximizing feedback at each step is not optimal. Our agent needs to consider how each action affects the future. Sure, okay, single agent reinforcement learning. Part 2 of these notes will introduce MDPs. They allow us to model reinforcement learning problems. We look at model-based techniques where the entire MDP model is known to us, and model-free techniques which are flexible enough that when some information is not provided explicitly, but can be sampled through enough times, we can still learn good behavior. We will look at the foundational techniques, some more advanced techniques, and we'll pay particular attention to how to scale reinforcement learning so we can use it to solve real problems. Multi-agent reinforcement learning. In part 3 of this book, we look at multi-agent MDPs, sometimes called games, in which there are multiple, probably adversarial agents in a problem, and we need to plan our decisions while also considering the other actions in the environment we'll do. Again, we'll look at both model-based and model-free. Alright. My key understanding of this text is going to determine how well we can do when writing. Josh Raj is in chat, says, hey, are you something encoding things like AI and ML? Hey, are you there? Yeah, I'm here. So, I am coding right now for a subject that is AI related. So that's what I am doing, and I'm just going to be learning about single agent and multi-agent reinforcement learning. I'm going to build something in the multi-agent reinforcement learning section, and we'll see how well that goes. That'll be the aim for part of this stream. If I can understand pretty much all of these subsections. Okay. Alright, so getting started with the first example, the learning outcomes: gain a basic understanding of reinforcement, have a practical experience in building a reinforcement learning agent using deep Q learning, and be excited about reinforcement learning and its possibilities. Oh, Josh Raj. Actually, we're looking for someone like this for a new startup. So you're good to go, then please let me know. Alright, no worries. I mean, join the Discord if you want to chat further. We can. I'm open to anything. But yeah, we can talk about this later if you want. Okay, so overview. Before we start on the basics of reinforcement learning, let's build an example of a reinforcement learning agent. We'll use reinforcement learning to play Atari games. Atari was a game consoles manufactured in the 1990s. Their logo is shown in Figure 1, the arcade learning environment built on Atari 2600. Emulator Stella is a framework for reinforcement learning that allows people to experiment with dozens of Atari games, built on the popular Gymnasium framework from OpenAI. Gymnasium framework. Sure. Play Freeway. Freeway is the Atari 2600 game that we will begin with. In Freeway, a chicken needs to cross several lanes on a freeway without running over by a car. A screenshot of the game is shown in Figure 2. Each time the chicken crosses the top, we gain 1 point. If the chicken is struck by a vehicle, it goes back a few spaces, slowing it down. The aim is to cross the road as many times as possible in the allocated time. This is a simple game as far as video games go and as far as reinforcement learning goes. However, let's train a reinforcement learning agent to play it. So this is a single player game, but you know, we need a multiplayer one at some point. But okay, screenshot of the game, Freeway, yada yada yada. Right, so import components from the reinforcement learning framework. So we're going to use Torch. It's a good question if we do use Torch at all if we're allowed to use Torch at all for this assignment. I think we are, from my understanding, because if I look at the allowed, yes we are. Okay, we are allowed Torch. Yeah, we're allowed Torch, but it's of a specific version that we probably should use TensorFlow CPU. So Torch 2.0.1 plus CPU. That's very, I guess the plus CPU might mean you can only use your CPU for when using Torch. Possibly. Plus. Mooch says, is this for uni work or extra learning? This is for uni work, but I still like it. And this is technically extra learning for an assignment. You know, I'm learning about reinforcement learning and trying to implement something. Okay, but PyTorch versions. So I'm guessing, you know, if you don't specify, or if you do specify CPU, then it means that you're using only CPU when using Torch. PyTorch. Okay. Maybe it matters, maybe it doesn't. I really wouldn't know. Okay. First we need to import some stuff for the deep learning package and some settings. Import if the CPU is to be used, device, Torch device, CUDA. If Torch CUDA is available, alright, yeah, so just use it if you have it, and set the default device to that device. Okay, the first line above simply imports Torch from the PyTorch Deep Learning Framework. This is not a framework specifically for reinforcement learning, it's a general deep learning framework for production code, which we can use as part of our reinforcement learning solution. The rest set up the device to use. If our machine has a GPU, then using CUDA, we'll use that GPU for doing matrix calculations in our deep learning model. If our machine does not have a GPU, we can use the CPU instead. A GPU will allow us to train more quickly, but otherwise we get the same results. Next, we import a few other things that are part of the reinforcement learning framework written for this book. We import a few other things that are part of the reinforcement learning framework. So the reinforcement learning framework, I'm assuming that's just, you're talking about PyTorch here. And experienced replay learner, I would expect to come from PyTorch. Maybe not. Maybe not. They did say in their foreword about the code, you can download the code here. Sure, so that's the code. Oh, whoops. Josh Raj, no problem. I'll check it out later. Okay. Python code, deep queue function, grid worlds, lots of utilities here. They could have just put this in like a repository, but I can get it. These are academics we're talking about. You can download the code. The code is in the book and is written for understandability rather than efficiency. It is not intended to be production level. If you understand the code and notes you have a little problem using production level packages, the code in the book is written for the intent to use very little Python specific syntax. The code in this book is written by a few external libraries as possible to make this easy to download and run yourself. Once you have downloaded, unzip the code and add it to your Python path if you want to download your notebooks. I have a main function that can run the Python file name for most of these. No external libraries are required, however. If you want to plot the graphs or trees, you'll need to install these extra utilities. So I think that would make sense then. This comes from that from here. So maybe I should just export this. Alright. Extract to code. Python code. And probably gonna rename this Do I want to open it in WSL, however? Doesn't matter. Maybe not. Maybe not. Okay. Probably just best to open a new window. You should be looking for Experience Replay Learner. Experience Replay Learner, here we go. Experience Replay Learner, deep queue function, multi-arm bandit, epsilon decreasing, ALU wrapper. Is the reinforcement learning algorithm that we'll use for this example. It uses a deep queue function. Deep queue function. Well, that seems pretty fitting, given that our assignment is to create, a reinforcement learning that is either a classical, approximate, or deep queue learning. So deep queue, I think that, okay, these are going to be useful. Okay, Experience Replay Learner is the reinforcement learning algorithm that we'll use for this example. It uses a deep queue function to learn the value of different actions in the game. Depending on the context of the game, it is a variant of deep queue learning. Okay. Okay, we'll take a closer look at this. Close that, close this. So we can keep that open. Effectively, the way Experience Replay Learner works is that it plays the game a number of times, then samples some of the moves from those games and works out how good each move was based on the score of the game that move was played in. Then uses machine learning to learn a predictor, a deep Q function in this example, for how good other moves are in other contexts. Using the machine learning predictor, the Experience Replay Learner plays the game a bunch of times. Again, hopefully better this time because it knows something about the game. Then it again samples moves and updates the machine learning predictor. It repeats this process until it has played a certain number of games. We will use 30 games for this example. It comes from the fact that the agent first plays the games and then replays them back again to learn. You can learn more about this in Experience Replay. Okay, Experience Replay. Okay, well there is nothing here, sure. Okay, epsilon decreasing is a multi-arm bandit algorithm. These are important in reinforcement learning. For now, just know that what this does is help us explore different moves of the game so that the player's experiments help it learn. And finally, ALE wrapper is a simple wrapper class, the arcade learning environment that we use to play. Set up the learning environment, the version, the policy name. So I see you can have some policies here for sure. Hello KFC, thanks for joining. Okay. So the version is the game that we're going to play. In this case, three-way version 4, which uses the ramp to represent the problem. We can also learn directly from pixels, but for now we'll just keep it simple. Finally, we can create our environment, which is called MDP, Markov Decision Process, which is the model that describes reinforcement learning problems. Set up the learner. Okay. Train the agent in reinforcement learning. Now that we're ready to set up our learning algorithm, the following 5 lines are all it takes. Action space. Get actions, get initial state. Is this similar to what I see here? Should be. My agent, actions, game state. Experience Replay Learner, MDP, epsilon decreasing policy Q function, target Q function. We'll create the 2 deep Q function instances. The reason for this describes in Experience Replay, but for now, what is important is we have one called policy, which is the machine learning model that will be choosing moves during learning and will also form the basis of our policy when we have finished learning and create a player to just play the game. The target Q function here helps the learning, but it's then not used again. Both of these deep Q function. Okay, so it's just cuts off there for sure. Okay, we create the Experience Replay Learner by passing it in the environment that it will learn from. multi-arm banded algorithm, epsilon decreasing, and the two deep Q functions. Okay. MDP. So this MDP comes from nowhere. Oh, okay. Right. ALE wrapper. So finally it is a simple wrapper for the arcade learning environment. Used to play free play. Okay. So Q policy, Q function. Neuronervous was declared in the environment. Okay. Play it. Speed it up. Ooh. Okay, never mind. Trying to see if I can speed it up. Just doesn't move, it seems. Too scared to move. We create two deep Q instances. The reason for this are as described. Okay, so we create the experience replay learner by passing it the environment that it will learn from, the multi-arm bandit, and the two deep Q functions. Policy Q function will end up being the basis for our policy after we have finished learning. For now, it's just a deep learning model with random parameters, so it does not do anything useful. We'll use this to construct a policy for our agent to use. Policy function. We save the policy to a file so we can use it later without having to retrain the agent. Let's watch it replay freeway by creating a GIF of it playing. Right, so it does nothing. As you can see, it does not so well because we have not yet tried to learn any behavior. But we are ready to start learning. So we haven't learned anything yet. Okay. Training the agent with reinforcement learning. Next, we'll need to do the hard work, training the agent. This should be difficult to code, right? This is where the learning actually happens. Well, not so difficult to code once we have a good framework in place. Rewards equal to the learner.execute episodes 30. The execute function is what runs the games, collects the experience, rates the quality of the moves, and puts the right data into the deep Q functions. Deep Q functions, we need to specify how many episodes games it should play. In this case, we choose 30 games. It returns a list of rewards, in this case, points in the game received at each step. Now we can construct a new policy for our agent player to use. This is easy enough to do. Remember the policy Q function? That has learned a Q function, which simply tells us that each step of the game, the estimated value of each of the possible moves. Here value is just saying, at this step, I think action up will, on average, give us a score of 10. We can now just put that inside a policy class, and we can save the policy for future use. QPolicy provides a function called selectAction, where state is the current step of the game and actions are the set of applicable actions. All selectAction does is iterate over the actions and returns the one with the highest estimate. That's it. Now we have a trained player that can play freeway. Let's have a look at how it goes. So we load that policy and we create the GIF, and this is the GIF. Not bad. Not bad at all. We can also study how well the algorithm was learning during the learning process. The following graph plots the number of words, number of times the chicken makes it to the other side. It looks like a kangaroo, just saying. Okay. You can see how it looks like a chicken actually also. Not like a kangaroo. So you can also study how well the algorithm was learning during the learning process. The following graphs plus the number of words, number of times the chicken makes it to the other side of the road in this case, and received against the number of games that has been played. So cumulative reward over the number of games that has been played. Okay. So it does increase. I guess that's the main information to get out from that graph. The test.plot, import plot. I'm guessing that's also in here. Tests. Yeah, tests.plot. So plot is here. Good. It's good. Okay. Example playing Frogger. Let's build another one, but this time to play the game Frogger. Okay, Frogger. It really is quite a similar game. Okay, this is a very simple game. Instead of a chicken, there is a frog. The frog has to get to the other side of the road and river. If the frog is stuck by a vehicle, it loses a life. Is struck by a vehicle, it loses life and starts back at the beginning. Once it gets to the river at the top, it needs to jump onto the log and other floating debris to get to the other side of the river. It falls into the water, it loses a life and starts back at the beginning. It has 3 lives in total. First thing to do is create an MDP for the Frogger game. Okay. Policy. Man, okay, I need to have a look at this ALE. What does this actually mean? Frogger policy. ALE Frogger RAM 5. Multi-arm bandit. Layouts. Rope project. Okay, well, I can't see ALE anywhere here. ALE wrapper comes from what exactly also? Could come from ALE wrapper. Okay. Oh, Sabodo Walnuts, hello. Thanks for joining. Okay. So everything is the same. We get the action space and state space. Policy queue function. Target queue function. As with freeway, let's watch a policy that has randomly initialized parameters first. Okay, and that should just be not moving at all. Yeah, which is it's died. Yeah, it's died multiple times. That looks like a death to me. Okay, so Frogger is simulated. Now we can see that it does quite poorly, but let's train this for 30 episodes. Let's see how it goes. For 30 episodes. Okay, it's going way too fast here. Let's see. Not much better. What's happening? Why does it not work for Frogger, but it works for Freeway? Freeway, the answer is Freeway just has 3 moves, up, down, and stay. Frogger has up, down, left, right, or stay. As such, running for only 30 episodes does not give the learner enough space to learn good behavior. Which makes sense. So what if we train it for more episodes? Here's one that I prepared earlier, which is trained on 2000 episodes and ran overnight for several hours. We should expect this to be better. Okay. Okay, yeah. Gets close, doesn't it? So this is much better. It does not reach the other side, which would presumably require another few thousand episodes or a better learning algorithm. Okay, we looked at training a couple of simple play games. Simple, okay. Single player games to play 2 Atari games. Maybe it's simple. Maybe it's simple. These worked okay. Depending on the properties of the application, some types of reinforcement learning algorithms work better than others. How do the algorithm learn what they do? Which learning algorithms are best for which type of application? Is the rest of these notes? Yeah, in the rest of these notes, you will learn more about this. Pulling together an agent that learns is not difficult when we use an existing framework. But more complex the application, the more computation time it takes to train. In the game of Azul, which is the game that we are building for, it's going to be a little bit different. Because Python general game runner -g of Azul -a of agents dot generic dot random to against an agents dot generic okay, so agents dot t 0032 dot my team -t and -l. Right, okay, so source then bin activate, and we should get that running, no problem. -t is just a terminal. So we want -l only for now. This is the game of Azul against 2 random agents that pick actions randomly. And ideally, you know, we just need to find a way to pick the correct action enough times so we can win against a random agent, at least. Okay. Let's see. I say? What can I do here? Okay, Markov decision processes, a definition of it. And so an MDP, get transitions, get goal states. Value-based methods, we have multi-arm bandits, key function approximation, policy-based methods, policy iteration, policy gradient, actor critic methods. What? Okay, multi-agent reinforcement. Okay, in the following chapters, we look at games. By games, we do not only mean games of chess or digital games. The term game is a more general term to describe a problem that involves multiple agents or players. The standard definition of an MDP is for a single agent. So the standard definition is for a single agent who controls all of the actions. In a multi-agent system, we face further challenges, which is the effect of actions and the rewards we receive are dependent also on the actions of the agents. In fact, the other agents can even be our adversaries, so they may be working to minimize our rewards. First, we look at a normal form game, which is single shot, non-sequential games where a group of agents each has to play a move, execute an action at the same time as all others. But the reward or payoff that they receive is dependent on the moves of the other agents. So it seems, okay. I apologize for the loud noise. My parents are just speaking on the telephone, so you can imagine old people just speaking on the telephone very loudly. Anyway, regardless, hope it's not too disturbing. Okay, so normal form games seem to me to be just a single shot, non-sequential game. Makes sense. Then we have an extensive form game, which is a sequential game, meaning there are multiple actions played in sequence, which is the game of Azul and is what I need to look at. Okay, so the learning objective of this chapter is to identify situations in which a normal form game are a suitable model for a problem, manually calculate the best responses and Nash equilibria for two-player normal form games, and compare and contrast pure strategies and mixed strategies. Nash equilibria, this is literally, we're talking about like microeconomics at this point. So, because I remember talking about Nash equilibria in my economic subjects. I don't think that this would be informational for me in terms of this normal form games algorithms. So we will leave this section for now and go to extensive form games. Okay, so the learning outcomes of this chapter are to define extensive form game, identify situations in which extensive form games are a suitable model for a problem, define the types of strategies for an extensive form game, manually apply backward induction to small extensive form games, and design and implement backward induction to solve medium-scale extensive form games automatically. To solve medium-scale extensive form games. So something that I need to understand is, what does that mean in terms of a medium scale? Because personally, if Azul is not a medium scale game, then I'm fucked. It could perform worse than a random agent. So we'll see how we go. Alright, this is the uncertainty that we just have to live through. Okay. I'm gonna get some water and be right back. Okay. Alright. Alright, so this is going to be informative for me. It's going to be interesting nonetheless. The problem is, okay, what is goal recognition? Because there are some other possibilities that I could do that is not just reinforcement learning. Although I'm pretty committed to doing reinforcement learning. The other ones that we have are game theoretic methods, goal recognition techniques, infer intentions of opponents. You have reinforcement learning, which is classical or approximate or deep Q learning. You have Monte Carlo tree search or UCT, which by the way I've forgotten what UCT is. And then you have policy iteration or value iteration, model-based MDPs. Okay, model-based MDPs and classical planning for PDDL and calling a classical planner, those would probably take more computation and probably not the ideal. So my thinking is perhaps a model free MDP solver, such as reinforcement learning, or Monte Carlo tree search, which my friend has already done for his part, since each of us are doing separate stuff. I'm going to commit to reinforcement learning here, but it's going to be a little bit weird, I think. Alright, we'll see. We'll see how it goes. We'll see how things go. Let's see. Give me 1 second. Alright. Alright. Let's have a go. Alright. So, have a read through this. Take it step by step. So, in the overview, in this section we look at extensive form games. An extensive form game is a sequential game. It includes a set of players, rules around which players can move when, and what they observe, and the rewards they receive when they move. Okay. Yep, sounds like Azul. In an extensive form game, there are multiple players who take moves in the game, but not simultaneously. Yeah, fair enough. And at the end of the game, each player receives a reward known as a payoff, which can be positive or negative. So, sure, we will look at three main advantages or three main ways to solve extensive form games. Either in a model-based game, we can use the backward induction, which is where we calculate an equilibrium for every subgame of the game, and these to decide our moves. Okay. Sure, and in a model-free game, we use model-free reinforcement learning. These are simple techniques. These are simple techniques such as Q-learning. These are similar to techniques such as Q-learning or policy gradient methods, except that there are other players that can affect our rewards, rather than just ourselves and the environment. If we have a simulation, we can use model-free techniques or multi-agent Monte Carlo tree search. Which is similar to single-agent Monte Carlo Monte Carlo tree search, except again, there are other players that can affect our rewards rather than just ourselves and the environment. Okay, in these notes we'll look only at perfect information extensive form games. Perfect information, yeah, we do have perfect information, I think. Which means that the game state is fully observable to all players. Yeah, we do, basically. It's literally, you can see it right here. Perfect information extensive form games. Perfect information extensive form game is a tuple G, which is equal to NS S0 AAT and R. Number of players, states or nodes, initial state is a function that specifies the allowed actions from each state, which is 2 to the power of A. Why 2? So from any state S, maps to 2 to the power of A. It's a bit confusing there, so I'll just ignore it for now. Okay, but P from S to N, from the set of states to the set of number of players, is a function that specifies which player chooses the action at a node. Okay, yeah. TSA S is a transition function that specifies the successor state for choosing an action in a state. Makes sense. R from S to the real of, say, a 2-player game. I bet that's a set. Why would you use capital N there? So N tuple specifying the reward function that returns an N tuple specifying the payoff each player receives in a state. In some texts this may be called U instead of R to represent utility, but we will use R in these notes. An extensive form game forms a tree due to its sequential nature. Consider the following simple game called a sharing game from Essentials in Game Theory by Leighton Brown and Shoham. Imagine a brother and a sister following the following protocol for sharing 2 individual and identical presents from their parents. First, the brother suggests a split, which can be one of 3. He keeps both, she keeps both, or they each keep 1. And the sister chooses whether to accept or reject the split. If she accepts, they each get their allocated presents, and otherwise neither gets any gift.
Finish conversation?
Conversation?
You finish streaming?
No,
Oh, it's reading yourself.
I am.
But not on stream.
We can implement such a game in Python. First, we have an interface that defined what an extensive form game is. Then we need to implement this interface to create an extensive form game. We can visualize game trees. can implement such a game in Python. First, we have an interface that defined what an extensive form game is. Extensive form game. I wonder if we have that here. Don't have it. It's fine. Got a unique node ID to distinguish duplicate states. Then we need to implement this interface to create an extensive form game. Extensive form game. Azure resources. See, yeah. Okay, so not necessarily anything useful there. Not anything useful there. Wiki template is nothing. And yeah, it's pretty baseline. On who extended from Stephen Spratley. Fair enough, okay. Let's close that. Removed from clipboard. You can add and remove from clipboard. Yep. Requirements, template, details. Undo. Okay. Space X. Okay. We can visualize extensive form games as game trees, where the edges are actions and the nodes are states. The root node is the initial state. Instead of following extensive form game, the sharing game. The labels next to nodes indicate whose turn it is. B for the brother and S for the sister and the tuple. In nodes are the payoffs at that node, blank if there are no payoffs. Okay, sharing game. Node to graph. Yep. Solution for extensive form games. So like normal form games, extensive form games have strategies. However, the strategies must tell each agent what to do every time it is their turn to choose the action. Definition of pure strategy. For an extensive form game G, the pure strategies of player I is the Cartesian product. Therefore, a pure strategy for player I tells them what move to take in each state where it is their turn. Fine. Okay, as an example, consider the sharing game. In this case, the same game on the left and middle have two equilibria because the payoffs for each of the moves are 0 for the sister. In such a case, ties can be broken randomly, or we can take all best responses. Okay. So we said backward induction was only possible for model-based games. Let's do a model-free game. Monte Carlo. Research. You can extend techniques like Q-learning, SARS-RM, CTS from single agent to multi-agent in a straightforward way. Other more sophisticated techniques exist for true stochastic games with simultaneous moves, such as mean field Q-learning, which reduces the number of possible interactions between actions of approximating joint actions between all pairs of actions, rather than all global interactions among the agents. Okay. So the learning outcomes, describe the modeling and abstraction strategies to scale algorithms for multi-agent games. Apply modeling and abstraction strategies to non-trivial multi-agent games. Limited reasoning of opponent actions. Okay, I mean, this is like further on. I think this would get to the end of my understanding here. So this is literally at the end of the document. Okay, so this is what I need to understand. Multi-agent Q-learning. Multi-agent Monte Carlo tree search. Yeah, so this is what my friend did, presumably. And I'm going to try multi-agent Q-learning. Solutions for stochastic games. Stochastic games. And overview. Okay, the field of multi-agent reinforcement learning has become quite vast. Can I open issue? Open issue. Full file not found. Love the maintainability. What can I say? Let's see if we can open the repository. At least, nope. You can't even open the repository because, yeah, it's just not working. Okay, recall the idea of expected max trees. We're gonna still need to read this. Okay, so it has become quite vast, and there are several algorithms for solving them. We just going to look at how we can extend the lessons learned to the field in the first part of these notes to work as stochastic games, which are generalizations of extensive form games. Okay, stochastic games. So definition of a stochastic game, and to explain the difference between a single agent reinforcement and multi-agent reinforcement learning. So recall the idea of expected max trees, which we first encountered in the section of Monte Carlo tree search. Expected max trees are representations of MDPs. Recall that the white nodes are states and the black nodes are what we consider choices by environment. White nodes are states, black nodes are what we consider as choices for the environments. Choices, yeah, alright, fair enough. An extensive form game can be thought of as a slight modification to an expected max tree, except the choice at the black node is no longer left up to the environment, but is made by another agent instead. Yep, so this is what I'm more familiar with than this, but it makes sense what this says. From this visualization, we can see that an extensive form game can be solved with model-free reinforcement learning techniques and Monte Carlo tree search techniques. We can just treat our opponent as the environment, albeit one that has a particular goal itself. In this section, we just give the intuition of how reinforcement learning techniques can be applied in multi-agent settings like this. Extensions that are specific to multi-agent techniques also exist. So stochastic games is a tuple G where S is a set of states S0 is the initial state, A1 to AN. So AI is the set of actions for agent J. Sorry, AJ is the set of actions for the agent J, right? So for a two-player game, that'll be agent 1 and agent 2. Actions for 1 and actions for 2. You know, ideally these actions would be the same for both of these actors. So P S times A1 all the way to AN is a transition function that defines the probability of arriving in a state given a starting state and the actions chosen by all players. Yeah, okay, that makes sense. That's going to be like infinite, you can't really say what it is. Is the reward function for agent J, which returns a real valued number. And gamma is the discount factor. From the definitions, we can see two things. A stochastic game is simply a version of the MDP which the action space and reward space are tuples. Action and reward are tuples. It is, in fact, a generalization of MDPs because we can just set n equal to 1 and we have a standard MDP. Correct. Stochastic game is a generalization of an extensive form game. Yep, that is, we can express any extensive form game as a stochastic game, not vice versa, because for example actions in extensive form games are deterministic and multiple agents cannot execute actions simultaneously. However, we can simulate an extensive form game by restricting all but one player to playing just a null action that has no effect. Yeah, makes sense. Solutions for stochastic games. Here we go, here's the V value. Multi-agent Q learning. Multi-agent Q learning, okay. Have a think. In a stochastic game, the solution is a set of policies. One policy I, J, for each agent J. Yep. The joint policy of all agents is simply the objective for an agent is to maximize its own expected discounted accumulated reward. Expected discounted accumulated reward. Expected discounted accumulated by summing reward. Yeah, I can understand how those values make sense there. Note that A is equal to ISI. So the policy at state is the joint action of all agents. Yeah, okay. So each agent's objective is to maximize its own expected reward considering the possible actions of all other agents. Multi-agent Q learning. Given the similarities between MDPs and stochastic games, we can recast our standard Q learning algorithm as a multi-agent version. Yes. So multi-agent queue learning is a stochastic game. So from policy-based methods, policy gradients, policy iteration, action critic, queue function approximation. Where's queue learning here at all? Temporal difference reinforcement learning, possibly. So temporal difference, model-based versus model-free. The mystery game. Monte Carlo reinforcement learning. Queue tables. TD reinforcement learning. Queue learning, off policy temporal difference learning. Updating the queue function. Policy extraction and implementation. Grid world example, SARS on policy, temporal difference learning, implementation, yada yada yada. Q learning, SASA. Yeah, we already know these. So learning on the job, again, that's actually something that's useful to know. Okay. Okay, wait, SASA is good for offline, right? That's let me look at that graph again. So right, I gotta look back at my notes here to convince myself. Okay. Zoom in. Once things load, to be honest, this does take some time to load. A large file, very large file. But, you know, we can see some of it already here. Hopefully I can zoom in and it won't be a problem. Okay. So, let's softmax. Okay, we actually are in the wrong space here. Should be around here when it loads. Ideally it loads. Ideally. Okay. Although just from my notes I can kind of understand. They're just loading slowly. Slowly but surely. Just gotta wait. However, here we go. Okay, so on policy TD, so on policy better when learning on the job. On policy is SASA. Q learning is off policy. So because we need to select the best action A in Q learning, using max A QSA, we iterate over all actions to limit Q learning to discrete action spaces. I suppose, yeah, it is discrete because we only have X number of hours to choose from. Oh, X number of actions to choose from, but where do you put? Right, so it's technically 8 by 5, still a limited number, but it's yeah, still something to think about. Okay. The number of states, however, is pretty extensive, I would imagine. Okay. Learning on the job, difficult to learn offline. Actions we take now can change other things later. Jobs coming in have to be learning. For example, scheduling algorithm. On policy is better at learning on the job. Off policy, learning from experience. And what happened there, right? Average reward per episode. That's still something I gotta understand. Let's read this. Okay. During training, SASA receives higher average reward per episode. With following then Q learning because it falls off the cliff less as its policy improves. Q learning agent will follow the path along the cliff but fall off when it explores. Meaning that the average reward is lower. However, Q learning learns the optimal policy, meaning that once we extract the policy, its rewards will be higher on average. How is it possible that on-policy learning has suboptimal policy but high rewards during training? Consider a case of two agents training, one with Q-learning and one with Salsa, both using epsilon greedy with epsilon 0.2. Then consider training episodes 100 for each agent. For the plot above, you can see that both policies are close to convergence. However, once training is complete, we extract a policy. Because the actions are deterministic, the Q-learning policy is optimal. Yeah, so it will follow the path next to the cliff, but it will not fall off. The Salsa agent will follow the safe path, but the safety is no longer required because no exploration is done. Is no longer required because no exploration is done. The ending result for the Salsa on policy method is suboptimal policy, because it also takes into account the exploration factor. So if that's the case, during training, you can train, using Salsa while playing the game. And then Q-learning, yeah, got to think about it. Okay. Back to this. Okay. Whew. Okay, so this is not going to be too much more intense once I understand all this. Just taking just need some time to rest soon. Let's see. I'll stop speaking for a bit. I'll just read this. In a stochastic game, the solution is a set of policies, one policy for each, and then earn expected discounted accumulated reward. Okay, multi-agent Q-learning. Given the similarities between MDPs and stochastic games, we can recast our standard Q-learning algorithm as a multi-agent version. So there's multi-agent Q-learning, and yeah, the thing is I needed a Q-learning function just to compare with. That's Salsa. Q-learning. Here we go, okay. So we got Q-learning here. We got Salsa. Okay. Okay. Alright, here we go. Q-learning and Salsa compared. Stochastic game, MDP. Function, the self-agent, arbitrary, and we repeat. However, observe reward and new state until the end of the episode. It converges. So this is just the same as standard Q-learning. This will learn well because it's a model of NDPs. General enough for the opponent's actions to just be approximated as the environment. Okay. Now if we want to solve for just an extensive form game where players take turns, we can modify the above algorithm slightly. make the opponent's move more explicit. And by modifying the execution and update parts of the algorithm. So you're just taking into account more rewards rather than your own. This algorithm differs from the first in two main ways. After executing our action, we do not observe the next state immediately, but instead we wait until it's our turn again. Observe state Tn, where n-1 moves has been made by other agents. Observe all rewards that we have received over the sequence, including the other agents. These two algorithms are equivalent for an extensive form game. However, rather than simulating null actions for an agent, when it's not their turn, it is often simpler and less computationally expensive to instead use the latter. Okay, these algorithms work well as the learning is independent of all the other agents. This is known as independent learning. However, it assumes that all the other agents' policies are stationary. That is, assumes that the other agents' policies do not change over time. This is a limitation, but there are several techniques that do not make this assumption. However, we can discuss ways to model our opponent for improving multi-agent queue learning. Okay, so like some of this content is actually useful to keep as highlights. These algorithms work well. Oops. This is also information. Sorry, 谢谢吧。
没事。
现在几点？左右。It's already 5:16 here. Okay. course, it is not just Q-learning that can be extended to the multi-agent case. The main question we need to answer is, how can we decide our opponent's moves if we are learning offline? In a truly model-free problem, we cannot simulate our opponents. However, our opponent will be executing their own moves, so we don't need to. However, we are learning in a simulated environment without real opponents. If we are learning in a simulated environment without real opponents, we'll need to simulate their moves ourselves rather than just waiting for their actions. How should we choose actions from opponent moves? There are a few ways to do this. Random selection, using a fixed policy, self-play. Okay, well that's actually very informative as well. Just as we extend Q-learning for a multi-agent case, we can extend Monte Carlo to the multi-agent case. Just a small change in our algorithms. So multi-agent MCTS is similar to single agent. We simply modify the basic MCTS algorithm as follows. Select. For our moves, we run selection as before. However, we also need to select models for our opponents in multi-agent MCTS. An easy way to do this is via self-play. Each node has a player whose turn it is. And we're using multi-armed banded algorithm to choose an action for that player. Expansion, instead of expanding a child node, we expand our actions, which leads which leads to our opponent's node. In the next iteration, the node becomes the node of expansion. Simulate, we then simulate as before, and we learn the rewards when we receive them. Recall that the rewards are a vector of rewards, one for each player. And then we backpropagate. The backpropagation step is the same as before, except that we need to keep the value of the node for every player, not just ourselves. Solving extensive form games in a model-free or simulated environment, we can extend techniques like Q-learning, SASO, and MCTS for single agents to multi-agent environments in a straightforward way. Other more sophisticated techniques exist for true stochastic games with simultaneous moves, such as mean field Q-learning, which reduces the number of possible interactions between actions by approximating joint actions between all pairs of actions, rather than all global interactions among agents. Okay, that's probably enough reading for now. Let's try. Now, take a closer look at this function. Okay. Might have to take some of this, you know, and put it here. Bottom. Okay. Okay. Trying to see what I could utilize here. Model free learner, right? Just gonna put this on the side, put this on this side. So we need a model free learner. Which is gonna go here. Why is this the case? Okay. Temporal difference learner. Okay. Say you have temporal difference learner. Keep the abstract there for now, actually. And notice a slight difference in the update from algorithm 4 and the update in the code delta. Q learning algorithm. So I suppose. Does most of the work all the Q-learning class has to do is define what the value of BS for the new state S. Which the state and the next action will be executed. Why do we model it like this instead of just implementing all of this in a single algorithm? We'll see why. Using the implementation, we execute 100 episodes on the grid world example, resulting in the following Q function. be right back. I gotta do something. Gotta prepare dinner. Help Dad. Be right back. Maybe 5 to 10 minutes. Be good to take a break as well. So, alright, be right back. Man. Cooked. Okay. My team. Ideally, we don't use random. Man, this is huge. Good world. I suppose. Game of Azul. Damn, dinner's already ready. Alright. I'm gonna go eat. In which case I might just end the stream, call it a night, and I'll possibly stream tomorrow. I think I will. Okay, thanks for tuning in, whoever's here. And yeah, man's gotta eat his dinner. His dinner. Alright. Catch you later.